Alright, so hopefully that little video is a nice review and reminder of what the phrase half-life means. So I know that you've done half-life already. You did it in earth science. Whether or not you remember it very clearly is another story. So we're going to refresh what it means, and we're going to really see it in a chemistry kind of way. Now the good thing with half-life is there are no formulas for half-life. We're going to use a chart method to do most of these questions. They are, generally speaking, word problems, so do be prepared to read carefully. All right, so right here we've got our definition of half-life. All right, so it is the period of time that must go by for half the nuclei in a sample to decay. And as you saw in the little clip there, carbon-14 has a specific half-life, and every other radioactive isotope has a specific half-life that either is listed in your reference table, or if it's not listed, you would have to determine the half-life, and that would be the point of the question you'd be given. But other than that, every single radioactive isotope that you're going to deal with essentially is found in your reference table with a listed half-life. So during a half-life period, half of the radioactive nuclei in a sample will decay. So it would decays into another thing. So essentially what we're doing with half-life is saying this is natural transmutation. This is our natural decay, and this is how long it takes for what particular radioactive isotope we're using. Now, I told you that they all have a specific decay mode, and that specific decay mode is listed for you right in your reference table. Now, those decay modes are actually found right on table N. So I'm going to ask you to pull out your reference table and make sure that you can find table N. And I actually have it right here for you. Okay, so it looks like this. It's the same table that we've been using throughout this that shows us our decay mode. It's also going to show us this part right here, which is the listed half-lives of each of the things that we're dealing with. Okay, so these are the nucleotides, so basically just the element that's going to decay. The half-life they're going to be using in days, years, minutes, seconds, whatever the case may be. A name, decay mode, so that you know where it is. Okay, so I'm going to keep that at the side. Now, what's very important for us to remember here is this. We have to realize that a half-life is a constant. Okay, that half-life is something that can never be changed. Okay, you can't do it. The other weird thing about this is that we can actually never decay to zero. So we're just going to constantly be cutting our amount in half. And if you keep doing that, I mean, it might seem like you get close to zero, but it's just like you reach a limit in math class. You can't quite hit zero. You have an asymptote, so to speak, okay? So there's, no matter how small it is, it's never quite going to be zero, though it seems like it might basically be zero. Okay, so how we're going to work this today, I'm going to do some examples for you, and then I'm going to leave some for you to finish up for homework. And I've broken down each of the types of the half-life problems into what their specific questions ask you. There are several different ways I can ask a half-life question, and so we're going to go through a bunch today. All right, so the first kind of half-life question I can ask has to do with elapsed time. All right, so right here. How much time has actually gone by as an amount of radioactive isotope decays. All right, so I have set up what I'm going to call an HTA chart. So I have the H with the half-life, the T with the time passed, and the A with the amount remaining. And we can basically use an HTA chart for every one of these problems. We do just have to manipulate them a little differently sometimes, but ultimately we do the same thing over and over again with each one of them. So you'll notice that I have the first chart filled in. So I have a 0 here, I have a 0 for the time passed, and I have a 0 for the amount remaining. So how long will it take for our original sample of 30 grams of Rn-222 to decay to 7.5 grams? So the way half-life works here is after every half-life, half of my amount decays. So I start with 30, so I put that in my amount remaining. And at 0 half-lives, meaning no time has gone by, I still have my original amount, no time has passed, and I haven't undergone any half-lives. But as soon as one half-life goes, I undergo one half-life, and I undergo the amount of time that a half-life has. I cut my amount in half. So instead of having 30, now I have 15. If I can never write 15 on here. There we go. All right, so basically I've said times 1/2, or I've divided by 2. Divide by 2 as we move over this way, okay? And then again, if I want to divide by 2 again, I'll get 7.5 after my second half-life. Now, that means that I've undergone 2 half-lives, so now I need to know how long a time that is. So I need to go to my table here. Oops, it's going to show through. And I'm going to find RN222, and I'm going to find that 1 half-life is 3.823 days. So if I need 2 of those, I multiply that time by 2, and I'll get that 7.646 days have gone by. All right, so then I just multiply through by however many half-lives there are, and I see how much time has passed. So this chart's really nice because you can see everything that you need, and it's that there are 2 half-lives gone by, 7.646 days, and I have 7.5 grams remaining, and it's all nice and concise and in one place. All right, now for the next one. How long will it take for a 28-gram sample of 226RA to decay to 3.5 grams? So let's do this one together again. And so we're going to do an HTA. It's like this. And I know that I have RA226. So I'm going to immediately look down and see what my half-life should be of that. So I'm here. I see RA226, and I have 1,599 years. That's a while. So my half-life is this. All right, so how long will it take for me to get from 28 to 3.5? So what I'm going to do is write out my chart, and I'm going to start at my 0 half-lives and not worry about my time yet and say I'm starting at 28. Undergo your half-life. So after 1 half-life goes by, I get 14. 2 half-lives go by, I get 7. 3 half-lives go by, I have 3.5, which is exactly what I wanted. Now it's time to see how many half-lives. 1, 2, 3 half-lives. So I take this times my 3 half-lives, and I'm going to see what I get, and that'll be my answer. And ultimately see that we have 4,797 years. Okay? That's how long it's going to take to get from 28 grams to 3.5 grams. That's a really long time for a very small amount of a radioactive substance, so keep it in mind. All right, number 3 I would like you to circle, because number 3 I'm going to ask you to complete for homework tonight. Okay, so don't do it now because I'm going to move on. We're going to do another type. So you have 1 question to do from the time remaining. You have 2 examples. So I hope you are successful in doing that one. All right, so the next type of question that you can see here is amount remaining. So I can ask you a question where it says, how much is left after a certain amount of time, given this particular compound? And so for a question like this, you must look up the half-life, and you must realize how much time has gone by. All right, so we're still going to use an HTA column. It really is the best way to go about this. So we're going to set up our HTA, half-life, time, and amount remaining. All right, so right now I'm going to see here. I have nitrogen 16, and I have 16 grams of it after 21.6 seconds. So the first thing that we're going to do is take a look at the table here, and we're going to figure out what the half-life is of that nitrogen 16. So hopefully you're doing this with me right now. So we have our nitrogen 16, and we have a half-life of 7.13 seconds. So I'm going to jot that down. Whoops-a-daisies. There we are. So 7.13. So what I'm going to do is take my 21.6, the time elapsed totally, and I'm going to divide it by the time that I know my half-life is. So I'm going to go 21.6 divided by 7.3, and you can pretty basically estimate it, that it's going to be approximately 3 half-lives. So 3 of my times that it takes for half of my sample to decay go into the amount of time that has elapsed. So I'm going to set up my chart for 3 half-lives. So I know I start at 0, 1, 2, and 3. So I have enough time gone by in this question for 3 half-lives to elapse. All right, now I have to figure out how much is going to remain in those after those 21.6 seconds. So I start with my original amount, which is 16, and then I go down by a half each half-life. So I divide by 2, and I get 8. I divide by 2, I get 4. I divide by 2 again, I get 2. So after 21.6 seconds, I have about 2 grams remaining, and that's my answer. All right, so I'm going to ask whoever's in here to please pause me right now at number 5, because I would like you guys to give number 5 a chance. So set up your HTA, see how many years you've got, how many grams are left over from this sample. So basically I want you to divide the time that has gone by the half-life, see how many half-lives have elapsed, and then figure out how many samples have gone. All right, so hopefully you have given it a try. So we're going to go through it together now, so please check your work. So I'm going to first set up my HTA, my half-life, my time, and my amount remaining. All right, so I'm dealing with larger numbers for this one, unfortunately. And those larger numbers are here for thorium-232. So I've had 9.8 times 10 to the 10th years go by, and my half-life of thorium is down here at also a 10 to the 10th, right here at 1.4 times 10 to the 10th years. All right, so that's nice because actually I can just kind of ignore the scientific notation because they're both 10 to the 10th. I can really just deal with the decimal in front. So I can go that after 9.8 times 10 to the 10th years divided by my half-life, which is 1.4 times 10 to the 10th, I will get my number of half-lives that can fit in that amount of time. And it is a nice, perfect 7 half-lives. Okay, so we know that we have 7 half-lives to go through here. So what we're going to do is leave space for those 7. So we're going to go 1, 0, 1, 2, 3, 4, 5, 6, and 7. So 1, 2, 3, 4, and 7 half-lives. And then we're going to start with our 256. Okay, so I'm going to divide by 2 as we go here. And we're going to get 128. And then we divide by 2 again, and we get 64. We divide by 2 again, we get 32. Again, 16, then 8, then 4, and 2. All right, so after 7 half-lives, starting at 256, we have only 2 grams remaining after look how many years you've still got 2 grams remaining. All right, so turn the page, please, and circle number 6, because number 6 is also going to be your homework for tonight. Okay, so make sure that you can get number 6 done. It is exactly like the 2 that we have just gone through. All right, so next we have a type of half-life question where they ask us about the fraction remaining. So you may have noticed as we've gone through these that I'm saying divide by 2, divide by 2, divide by 2 as we go through each half-life. So we can really think about that as the previous half-life being half of what's gone on. So I can say, oh, I have 1/2 of my original after 1 half-life. Oh, I have 1/4 of my original after 2 half-lives, and so on and so on and so on. And some questions really just want that as your answer. So it's really almost simpler when you think about it, but we don't have to use any specific numbers for them. We just use the fractional amount that is remaining. All right, so let's take a look at number 7. What fraction of a 100-gram sample of K42 will remain after 24.8 hours? Well, the first thing that you need to know is the half-life. So let's take another look at K42. It's right here. we have 12.36 hours for every half-life. All right, so jot that down, 12.36 hours. All right, and we have 24.8 hours that have gone by. So clearly you can see that we have almost exactly 2 half-lives. 24.8 divided by 12.3 equals just about exactly 2 half-lives. So 2 half-lives go by in this case. So I'm going to set up my HTA. So my half-lives, my time, and my amount. But I'm going to deal with fractions. So I know that I have 2 half-lives that go by, so 0, 1, and 2. Now I know that I have a 100-gram sample. That's great, and I could plop 100 grams right in there, and I think I will. So I'll put 100 grams there. After 1 half-life, I divide by 2. That's 50. After 2 half-lives, I divide, and I get 25. Now we know that 25 is 1/4 of my original sample, because 25 out of 100 equals 1/4. But say these numbers weren't quite so nice. Say these numbers weren't quite so simple. You can always just do this. I'm going to erase the 100, the 50, and the 25. And instead of doing that, I'm just going to assume I have 1. My entire whole sample, a whole 1, as just what I start with. Then I take my original sample and I divide it by 2. Now I have 1/2 of what I started with. Then I take my 1/2 and I divide it by 2. Well, what's 1/2 divided by 2? 1/4. So I immediately know that the fraction that's associated with 2 half-lives is just 1/4. And if I were to go on and on and on, I would get the same fractional amounts as we go. So yeah, we know we can do it like this and get 1/4, but also know that the same fractions will go with the same number of half-lives every time we do this. All right, so I'm going to ask you to take a look at number 8. Please pause me right now and give everyone a chance to attempt this on their own. All right, so hopefully you tried that one. So now what we're going to do here is go through this guy. So what fraction of a radioactive sample of iodine-131 would remain after 32.28 days? Well, again, the first thing we have to know is the half-life of iodine. So iodine is right here, whoop, right there, and it's 8.021 days. So 32 divided by 8.021 is obviously going to give us just about 4. So 4 half-lives is what we're dealing with. So we're going to set up our HTA. Okay, so we need 4 half-lives in here. Okay. And then at the start, we have our whole amount remaining. They don't even tell you the amount you start with, so you assume 1 in this instance. Then I divide what I start with by 2, and I get 1/2. I divide that by 2, and I get 1/4 of my original sample. I divide 1/4 in half, and I get 1/8. I divide 1/8 in half, and I get 1/16. So 1/16 of your original is going to be your answer. So for a question like this, they didn't even tell you how much you started with. You do need to just assume the 1 to get your fraction. All right, so in case you hadn't guessed it, please circle number 9 and consider it part of your homework tonight. All right, so for our next type of question here, we are asked to determine what is the half-life of a particular radioactive compound. And so the trick with these guys is realizing that you can look at this table all you want, but they are not going to be asking you about a radioactive nuclei that is listed here. All right, so you've got to really, really understand that half-life is actually what you're solving for. So they're going to give you the starting amount. So we know that we're dealing with 50 grams, and we're actually dealing with technetium, but it doesn't really matter. And then they are saying that we have 6.25 grams left at the end. And so we have to go through the half-life progression and see how many half-lives it takes to get from 50 to 6.25. So we're going to set up our HTA, and this is really the best way to visualize what's happening to you. Do you have to use the chart? Obviously, there are other methods, so if you feel comfortable doing this another way, go right on ahead. However, this is the way I'm going to show it to you. So I'm going to set up a bunch of half-lives because we're just going to have enough to keep going, okay? Because who knows how long it's going to take us. Then I'm going to put in my numbers 1, 2, 3, 4, 5, 6. And then if we need to keep going, we will. And then I'm going to put in my amounts. And so I know I start with 50, okay? But I know that after one half-life, I'm going to decay to 25, okay? After another half-life, I'm going to decay to 12. And then, hey, 12.5, I'm sorry. Then after my third half-life, I'm going to have 6.25, which is exactly what I wanted. And so I can take a look right there at the information I've got. After 3 half-lives, I have 6.25. But that's not what they wanted. They don't want to know, actually they do want to know how many half-life periods it will take. And so my answer here is 3 periods. Can't spell. There we go. 3 periods. So they are asking us just to determine exactly how many half-lives it will take to get to 6.25. So that's a nice one. All right. Number 11. Whoa. All right, so number 11, what it wants you to figure out is how many half-lives will pass by in order for 60 grams of cobalt-60 to decay to 7.5. So I'm going to ask you guys to give that one a whirl, see how many half-lives it takes, and unpause me when you want to see the answer. Alrighty, so let's set this one up. We're going to go right to our HTA table. Alright, so I want to get from 60 all the way to 7.5. Alright, so I'm going to set up my half-lives here. Let's give myself a good bunch. 1, 2, okay. And so I'm going to go from 60 over to 30 divided by 2, 15 divided by 2, and then, hey, 15 divided by 2 is 7.5. Once again, it takes me 3 half-lives to decay that amount. All right, circle number 12, it's part of your homework tonight. And then follow me, excuse me, to the next page. Alrighty, so we have 2 more types of question to get through. We have original mass, first of all. So original mass is weird because you're going to have to work backwards. So we're going to kind of keep that in our mind. So work backwards. We're still going to use our HTA table. We're just going to kind of use it in a little different manner. So if 2 grams of an original sample of gold 198 remain after 13.45 days, what was the original mass? So again, the first thing that we have to do is take a look at table N and figure out our half-life of gold. So the half-life of gold is 2.95, which is really nice. It's right there at the top for us. Okay, so we're right there. All right, so what we're going to first do is we're going to take the amount of time that's gone by, so that 13.45, and we're going to divide it by the half-life. So you can see that I did that right here, and you get 4.999, which is essentially 5 half-lives. All right, so we're dealing with 5 half-lives going by. All right, so what we're going to do is set up our HTA right here. Okay, and we're going to set it up for 5 half-lives. Okay, and then we're going to start with the amount that we know is left after 5 half-lives. Okay, and so then we're just going to work backwards. So if as I go this way across my table, I divide by 2, as I go the other way, as I go backwards, that means I get to multiply by 2. So what's 2 times 2? 4. 4 times 2? 8. 8 times 2? 16. 16 times 2? 32. 32 times 2? 64. And so I get to see that 64 grams is actually what I originally started with. All right. Okay, so what I would like you guys to do is give number 14 a whirl. See if you can set that one up divide your amount of time gone by the half-life of the uranium-235, and then set up your HTA to jump back to your original sample. Unpause me when you're good. Alrighty, so the first thing that you should be doing is looking at the table N, and figuring out that your half-life for uranium is right here. It's 7.04 times 10 to the 8th. And so what you're going to do is you're going to take that half-life value, and you're going to take the amount of time remaining, 2.84 times 10 to the 9th, and you're going to divide those two numbers. And ultimately what you get is that 4 half-lives have elapsed. So 4 half-lives. So if this were a question that we'd been doing before, 4 half-lives, that's all you'd need to know. But unfortunately, they want the amounts. So I set up my HTA here, and we know that there's 16 grams, 16.5 to be exact, that are remaining after those 4 half-lives. So we've got to jump back. And so in order to jump backwards, we undo the division of 2, so we multiply by 2. And so we get 16.5 times 2, meaning we have 33 grams. Multiply again, 66. Do it again, 132. Do it again, 264. So the amount that you originally start with is 264 grams. Hopefully that's what you got. Okay, circle number 15, it's part of your homework. All right, ladies and gentlemen, so guess what? We are going to save the last bit of these notes for tomorrow. So please just complete the ones that I've indicated for you as homework. So 15, 12, 6, and 3. And we will continue with the rest of this when I see you tomorrow. If you're confused, bring your questions. And I actually am in school today, so please come and see me. All right?